Hello. Hello. I'm going to share the video for chapter number 6, Atomic Structure. The contents for this particular chapter are as follows, and I'm going to show you the video and the PowerPoint presentation so that you can understand what is expected. In this particular chapter, the chapter outline are as follows. We will be doing electromagnetic radiation, quantization, Planck, Einstein energy and photons, atomic line spectra and Niels Bohr, particle wave duality prelude to quantum mechanics, the modern view of electronic structure, wave or quantum mechanics, the shapes of atomic orbitals, and one more electron property, electron spin. First, we go to the section. The goals for section 1. Mathematically, we relate the wavelength and frequency of electromagnetic radiation and the speed of light. Recognize that the relative wavelength or frequency of the various types of electromagnetic radiation. On subjection to different energy sources, atoms gain energy and become excited. This absorbed energy by the electrons is released in the form of electromagnetic radiation. Some of the known electromagnetic radiations are in the form of heat and light, energy which travels through space. These radiations consist of oscillating electric and magnetic fields traveling through space with the speed of light. The relation between the length of the radiation and its frequency is given by the expression C is equal to nu lambda. C is the speed of light, which is a constant. It is 2.998 times 10 raised to 8 meters per second. Wavelength is lambda, typically in nanometers, and nu is the frequency, and it is the units are second inverse or hertz. And here you have the general waves equations. Generally, we take them a unit of light as 3.0 times 10 raised to 8 meters per second. Nu is hertz or cycles per second. And lambda is the distance, of which we call as the wavelength. And here, the electromagnetic radiation or light is composed of two orthogonal factors, that is, they are perpendicular to each other, an electric wave and a magnetic wave. And electromagnetic radiation goes from one extreme end, that is the high energy, to the lowest energy. The higher energy is the X-rays and gamma rays, and on the other side you come to the radio waves that are there. And light is characterized by its wavelength and frequency. And here is the electromagnetic radiation spectra from gamma rays to X-rays, UV. There is a small portion which is the visible part of it, then IR, microwave, FM radio waves, AM radio, and long radio waves. And the frequency and energy increase as you go, and wavelength increases. So the relation between frequency and wavelength is an inverse relationship. And this is a typical example, because many of us do listen to the radio, and the wavelength of the radio waves from a particular station is 97.7 megahertz. Given that C is equal to nu lambda and mega is equal to 10 raised to 6, we can find out what is the lambda just by dividing C by nu and then substituting the value. Next, understand the photoelectric effect. Understand that the energy of a photon, a massless particle of radiation, is proportional to its frequency. And then what is quanta? In 1900, the German physicist Max Planck proposed that light, heat, and other forms of radiation come in tiny bundles, which he called quanta. The amount of energy in a single particle, he said, depended on the frequency and can be given by the following expression: E is equal to h. When you use the frequency of the wave, and h is a constant, and that came to be called as the Planck's constant. So E is equal to hc over lambda. The Max Planck proposed that light waves exist as discrete packets of energy, quanta, in order to